Yeah, 30.
Okay, let's get started. Homework is due today, homework 10. 10. 11 is assigned, but not yet due, so turn that in if you have it. This is it. All right, any others? There's a homework 11. 6:30. You wrote the wrong number on it. Okay. Any other homeworks?
Yeah, camera.
I gotta staple it. Hurry up!
She fails.
Okay, so today we're finishing chapter 15, and when we get back from the Thanksgiving break, we're going to move into chapter 18. Chapter 18 is not in your textbook, however, there's an online version of it that I have posted on MU Online. So if we go to MU Online in Blackboard, under Lecture Notes, there's a link here for you to see online chapter 18. So it's a pretty big file. I think it's around 56 megs, something like that. You'll have to download it. Probably it won't. Well, you can load it and look at it in the browser, but if you want to download it to your computer, then you have it. And chapter 18 is all about renewable energy. So it's a topic that I am excited about, and I think it's beneficial, and it's definitely something that should be covered in thermodynamics, because up to this point we've talked about, combustion and hydrocarbons and fuels, and we haven't even touched on the next wave of energy transfer, which is in these renewable systems. So if you have a little time over Thanksgiving break and you want to get started on the reading, you can look at the syllabus to see which sections we're covering. On the Tuesday after Thanksgiving, we'll start in section 18.1 and 2, which is about solar energy. So it would be a good idea for you to peruse that, just become a little bit familiar with it prior to coming to lecture, so we can have an engaging discussion about it. And, as always, if you have any interesting articles or information about things that are happening here in West Virginia with renewable energy, then I'm happy to see them. There are a couple of new companies that have actually come in the last couple of years, which is exciting to see. So that's online, so take a look at that. And we'll finish up chapter 15, and we'll be done talking about these fossil fuels for the meantime. Okay, so homework is due after the break, homework 11, and then there is an extra credit assignment. Both of those PDF files are in the homework section on Blackboard as well, so take a look at those. If you want to get it done before you leave for Thanksgiving, great, then you don't have to worry about it. So last time we talked about the first law analysis of these reacting systems, or these combustion systems, and we looked at the basically three separate cases. One is an open system, the second was a closed system, and then the third was adiabatic system. So if we look at an adiabatic system where we're assuming that there is some sort of a combustion reaction occurring, and this combustion reaction is releasing heat or absorbing heat, there will be a temperature change within the system, even if you're not transferring heat to or from the surroundings. So this adiabatic case was what we used in order to find the maximum temperature of a system, which is important. Why? Why do we care about that? You're just scratching. Okay, why do we care what the maximum temperature is going to be in our system? Why would that even be a concern?
Design purposes.
For design purposes, right? So we don't want to exceed the metallurgical constraints of our system. We don't want to have an unsafe system. So being able to calculate how hot this system will get and using that as kind of the upper limit for our design purposes is pretty important. So when we looked at these three separate cases, the closed system is basically the same as the open system, with the exception of this term here. Nothing works. What am I going to do if I get right on the screen? Okay. It's all right. It's all good. All right on the board. I need a pen if someone has one. Okay. So the closed system, ideal gas, if we assume that that the system is operating under the closed system assumption, then we use internal energy rather than enthalpy as our term. So we just subtract off from the enthalpy term that we have in the open system. So this is kind of backwards from how we've done it before, where we looked at the closed system first and then added on this PV term. Well, now we're just subtracting it off because it's easy to look up these enthalpies, much easier to find them sometimes than it is to find the internal energy terms. So that was what we talked about last time, and we're going to move into talking about the second law analysis of these systems, because we've looked at them from a conservation of mass standpoint. We've also looked at them from conservation of energy. Now we're going to look at them and say, okay, well, what can that do for us? How much potential energy can we get out of this system? How much irreversibility is there in this system? So we're going to look at it from a second law perspective. But before we do that, I want to go back to the last example that we did in lecture 23. And I'm not going to do the entire example, but there was a point at which we had this humid air coming into the system, and I sort of glossed over how to find how many moles of water are coming in, just because we were under time constraints. But I want to go through that example because I think it's informative and it will be helpful to you for your homework. So this adiabatic combustion process, again, it's adiabatic, meaning there's no heat transfer to the outside, so we set the two sides of the equation equal to one another. We have octane gas coming in, and then our byproducts are going to be water, CO2, nitrogen, and oxygen. And so in class last time, we set up the equation where we performed the balance and determined that the combustion equation, if it were dry air, is CH18 plus 16.25 times O2 plus 3.76 N2 goes to 9 H2O plus 8 CO2 plus 61.1 nitrogen plus 3.75 O2. So this is the combustion equation if we would just assume that we have dry air coming into our system. Okay, well in this problem statement it says explicitly that we have humidity associated with this air coming into the system. The good news is that this water is not going to react with any of the other components. So we don't treat it as a reactant necessarily. It's similar to nitrogen, where it just passes through the system. So the amount of water that we have and we add in on this side of the equation is going to be the same as the amount of water that exits on the other side. It's not going to react with any of these other molecules. So if we do the molar analysis for the dry air first, those numbers will stay the same with the exception of this number will change. And then we'll add a water component on this side of the equation. So you can do the analysis for the dry air first because that allows you to solve for these unknowns. Then you say, okay, well now I really have some water in the system, so I need to figure out how much. So what we do is we look at this, this process as if we're treating everything as an ideal gas, we can find the ratio of the pressures is equal to the number of moles times the gas constant times the temperature times over the volume of the vapor, and then the total, the same thing, N of the total times R times T of the total, and then the volume goes into the numerator. Okay, so if we look at this equation, the gas constant is consistent. The temperature is going to be the same of these components coming in. The volume is going to be the same. It's occupying the same space. So we're left with this ratio of the number of moles. So the number of moles of the vapor coming into the system divided by the total number of moles is equal to the ratio of the pressures. Okay, so now we need to find the pressure of the vapor. We know that it's coming in at 25 degrees C and 1 atmosphere. So if we go to our tables, we find for 25 degrees Celsius, the pressure of saturated liquid at that point is going to be the saturated pressure at 25 Celsius, which is equal to 3.1698 kilopascals. Okay, so that's the saturation pressure, but what we need to find is the pressure of the vapor. And from chapter 14, the pressure of the vapor is equal to this relative humidity times Psat. So our relative humidity in this case is 60%, so 0.60 times 3.1698 gives us some number 1.902 kilopascals. Okay, so now we know PV. Our total pressure is this 1 atmospheres, which is 101.325 kilopascals. We don't know the number of moles of our vapor, but we know that the total number of moles is going to be the number of moles of the air plus the number of moles of the vapor. We can find the number of moles of the air simply by adding them up. So it's 16.25 times 4.76. So N total is the total number of moles of the air is 16.25 multiplied by 4.76, which is equal to some number. I didn't actually explicitly calculate it. So we put everything together. So we have just one unknown, which is NV, and we can solve this in terms of the number of moles of water, or we can use a solver of some sort. If you solve it explicitly in terms of the number of moles of the vapor, it's equal to the number of moles of the air times PV over P total divided by 1 minus PV over P total. So all of these quantities are known in your equation. Solving for the number of moles of the vapor is 1.48. Okay, so that whole process was just so that you could equate this relative humidity to an actual number of moles of water that's coming into your system. Okay, and this is scanned and it's in the lecture notes for today too, so if you want to see that. So then going back to our original equation, we simply rewrite it, CH18, 16.25, and then we're going to add 1.48 H2O on this side of the equation, and then we change this 9H2O to 10.48 H2O on the other side of the equation. Okay, so again, you analyze the dry air case first. You go through this process to determine the total number of moles of water that is in your air coming into the system, and then you just add those to either side of the equation. That's how you account for humid air in these combustion processes. Okay. Any questions on that? All right. So that should help you understand that example a little bit better and also help you on your homework when it's time for you to do it yourself. Okay. So moving on to the new material. When we're looking at entropy change, the entropy balance for any system undergoing any process is just going to be equal to the entropy coming in minus the entropy leaving plus the entropy generated. Okay, so that's how you determine the change in entropy. That's just generic. It's for an open system, a closed system, steady flow, unsteady flow, any manner of system. We can look at it more specifically for a reacting system if it's a closed or a steady flow system. Now we have this heat transfer term in our equation. So we have the total number or the sum of the heat transfer divided by the temperature at which it occurs plus the entropy generated is going to be equal to the difference in the entropy of the products minus the entropy of the reactants. And if it is an adiabatic process, then we can set Sgen equal to the products minus the reactants. So this Q term goes away, and we simply have the entropy generation is equal to the entropy of the products minus the entropy of the reactants. we find the entropy of our products and our reactants, we have tables in the back of our book. If we look at the ideal gas tables, tables A18 through A24, something like that, A17 through A24, we have entropy in our table, right? But what's significant or what's different about this entropy that's tabulated that we need to remember? So like for example, in table A18, there's entropy there, but it's written like this. So there's like this superscript 0. What does that mean?
It's reference entropy, right?
Okay, so it's a reference entropy because entropy depends upon temperature and pressure. But every other property of these ideal gases depends on temperature only. So for a truly ideal gas, you only have to calculate the temperature to determine the enthalpy and the internal energy. But for entropy, it's also dependent upon the pressure, and in more particular, the difference between the pressure and the pressure at 0. Okay, so this is a reference entropy. So in order to calculate our actual entropy or our total entropy, we have to look at this correction factor. So we use our reference entropy, which we look up at the temperature and this P naught, or the reference pressure. But then we subtract off the universal gas constant times natural log of this molar fraction times the ratio of pressures. So P sub I is the pressure of the individual component. P naught is 1 atmosphere, and P sub N is the total pressure of the mixture. In the case where we're undergoing a combustion process, and for the most part, the pressure of our mixture is at atmospheric pressure, then we simply just need to find the natural log of this Y sub I term. So we have to calculate the molar fraction of each component in order to figure out this correction term. And then we simply just look up these reference entropy values from the tables. So it ends up being a lot more calculations within our system, because if you imagine you have, some hydrocarbon gas coming in, plus oxygen, plus nitrogen, then you have maybe 5 products on the outset. You have to look up a lot of property values for each of those individual components, and then add a lot of stuff together. So just like when we were doing the enthalpy balance, with the entropy balance, we have to be very, very careful about using the correct properties in the correct part of the equation, and then also as we punch everything into our calculator, that we're being very careful about that as well. Okay, so knowing the entropy change automatically allows us to figure out the exergy destruction, because exergy destruction is related to the entropy generation by T naught. So if we know the temperature of the surroundings, we can calculate the entropy generation using these tables and the correction factor. Then we can look up, or we can also find the exergy destruction. And in some cases, we're also interested in the reversible work. So the reversible work, or the equation for that, involves the enthalpy of formation, the enthalpy at the current state, the enthalpy of the reference state, minus this entropy term at each individual state. So this sort of is like the exergy destruction of each component, or the exergy state. Okay. Now, that brings us to a discussion of something called the Gibbs function. And if you look in table A26, you can see that for each of these hydrocarbon fuels, or in some cases just elements, there's an enthalpy of formation. But there's also this Gibbs function of formation, or this Gibbs function, along with the absolute entropy at 25 C in 1 atmosphere. So if the temperature of the reactants and the products are the same temperature as the surroundings, so if you have some dead state that's the same temperature as your products and your reactants, then we can use this Gibbs function in our calculations and in our equations for reversible work, rather than calculating the enthalpy and the entropy. And in the case where the reactants and the products and everything is an equal temperature, then it reduces further to just this Gibbs function of the reactants and the Gibbs function of the product. So these terms will be equal to one another, they drop out of the equation, and we simply have this equation. So when they're equal to one another, we can use this general equation, and when they're equal to one another, and that value that they're equal to is also 25 Celsius, which is the reference state that we use for calculating all these other properties, then those two terms go away. So if the surroundings are all at 30 Celsius, you'd have to use this equation, but if everything is at 25, then you could just simply use this Gibbs function equation here and calculate your reverse forward that way. Okay, so let's do some examples, and these, again, are scanned in the lecture notes. I apologize, I can't write on the screen today, so that won't be captured in the video, but it will be on the board here, and it's scanned and available for you. So again, these are some pretty big examples, 2 pages. It's not because it's very difficult, but just because we have a lot of individual terms to keep track of. So we have enthalpy for each of these reactants and products, and now we also have to look up entropy terms for each of these reactants and products. Okay. So example 1, we have liquid octane, C8H18, entering a steady flow combustion chamber at 25 Celsius and 1 atmosphere at a rate of 0.25 kilograms per minute. It's burned with 50% excess air that also enters at 25 Celsius and 1 atmosphere. After combustion, the products, leaving at 1 atmosphere, are allowed to cool to 25 Celsius. Assuming complete combustion and that all the water in the products is in the liquid form, determine the heat transfer rate, the rate of entropy generation, and the rate of exergy destruction. So we assume that our dead state is 298 Kelvin. Parts B and C are certainly related to one another. So once we find the rate of entropy generation, we just simply multiply it by T naught to find the rate of exergy destruction, which is kind of nice and helps us out a bit. Okay, to the board. I don't know if this microphone will pick me up, but I'll shout. Okay, so we have this combustion chamber with products, or with reactants coming in. We have air, and what is our air? What is the quality of it? What is it dry air? Is it just the right amount of air? What do we have coming in?
You have excess air.
Okay, we have excess air. How much excess?
50%.
Okay, so 1.5 times A theoretical is how much air we have coming in, and then we have a mass flow rate of 0.25 kilograms per minute on this C8H18. And they say specifically that it's in the liquid form rather than in the vapor form as it comes in. And why is that pertinent? What does that change in our calculations, or what does it mean?
Make the air wet.
There's no oxygen in it, so there's not going to be any water. Okay, so our enthalpy of formation
values we have to look up in the table.
That's right. Okay, so the enthalpy of formation values in table 826, there's a different value for liquid C8H18 versus gaseous C8H18. So you have to make sure you look up the correct value for that. And then we're told that we have liquid water coming out, and then we'll have our usual suspects, CO2, O2, and N2 at the outset. Okay, so we can perform our combustion analysis. So we have C8H18. We assume we have 1 kilomole of that coming in, plus 1.5 times the theoretical amount of air, which is O2 plus 3.76 N2 coming into our system. And then we have some amount of water in the liquid form, plus some amount of CO2, plus some amount of N2, plus 0.5 A theoretical of our O2, because the excess air just passes through the system. So we can perform some algebraic equations. We can figure out all the coefficients for this. So if we look at carbon, we have 8 carbons is equal to Y. And if we look at H2, we have how many H2s? 9 H2s is equal to X. Okay, so X and Y are easy to find. We look at O2, we have 1.5 times A theoretical on this side of the equation, and on this side we have what?
9.
X, is it X or, this is O, remember,
X
so this is
half.
O2. So X over 2 plus Y plus
0.58 theoretical.
0.58 theoretical. Okay, so this cancels that part out, so we have A theoretical is equal to X over 2 plus Y. So we do the math on that, we get it's 12.5. And then we solve for our Z term, so we have 1.5 times A theoretical, which we just found was 12.5 on this side of the equation, times 3.76 in front of that nitrogen is equal to Z. So Z is 70.5. Okay, so then we can rewrite and put these into our original equation, replacing the X, Y, Z, and A theoretical terms so that we know the coefficients in front of each of these. So in front of this, this 1.5 times A theoretical, we get 18.75. In front of H2O, we have 9 plus 8 CO2 plus 70.5 nitrogen plus 6.25 oxygen. Okay, so we balanced our equation, we have the correct number of kilomoles for each of those, assuming that we have 1 kilomole of fuel coming in. Okay, so this equation is 18.75 kilomoles of O2 per kilomole of CH18, if you wanted to put units on that. Okay, so now let's just start looking some things up. So we have CH18 in the liquid form. We're going to look up H sub F. We're also going to look up the entropy at 298, because this is 25 degrees C and this is 25 degrees C. So in this case, some things simplify out, and I'll write that. Okay, so we have O2, N2, CO2, and liquid H2O. So which H sub F for the CH18 liquid?
249,950.
249950 is negative. What about the S?
316.79.
Okay. O2?
0.
0. S?
205.04.
Okay. N2?
0.
O2. I mean, entropy. 191.61. CO2.
Negative 393,520.
And then our entropy.
213.80.
Okay. H2O liquid.
Negative 285,830.
285830, and our entropy is 69.92. Okay, ordinarily, we would look up H sub 0, which is at 298, and H of whatever the final product is, but in this case, it's also at 298. So if we look at our equation, minus Q out is equal to the sum of the number of products times the enthalpy of formation plus H bar minus H naught minus the sum of the number of reactants times the enthalpy of formation for each plus H minus H naught. Okay, in this case, our H value and our H naught are going to be the same. So this term is going to be 0 for every piece of the equation. So we could look those up, but we don't need them, so why bother? Okay, so our Q out is going to be the number of products times the enthalpy of formation for each of the products minus the number of reactants times the enthalpy of formation for each of those reactants. Okay, so what do we have for products in this equation? Which side of the equation is that? Okay, so right-hand side, so we have water, carbon dioxide, nitrogen, and oxygen, so we can write that out. So we have 9 times negative 2,85830 plus 8 times CO2, negative 3,93520 plus 70.5 times 0 plus 6.25 times 0. The enthalpy of formation for oxygen and nitrogen is 0. So this is the products minus the enthalpies of the reactants. So in this case, we have C8H18. We have 1 kilomole of that, and it's negative 249,950. And then we have 18.75 molecules of air, but those have 0 enthalpy of formation, so they don't end up in the equation. So negative Q out is equal to 547.0680. Actually, that's positive Q out. 547.0680 kilojoules per kilomole of the fuel. Okay, so we found Q, but in the problem statement, what does it actually ask us to find for Q? The rate of heat transfer. Okay, so how do we go from something that's in kilojoules per kilomole to a rate of kilojoules per second or kilojoules per minute? Do you have any kind of a flow rate?
We have mass flow rate.
Okay, we do. We have a mass flow rate. Can you multiply a mass flow rate times something that's in kilomoles and get a sensible value? With a few steps in between, right? So we need to convert it either all to kilograms or all to kilomoles. And in order to do that, we need to know the molar mass. So for C8H18, we can find the molar mass of C8H18. It's, I don't know if it's explicitly given in the book, but because we know the molar mass of carbon and the molar mass of hydrogen is just simply equal to 8 times the molar mass of carbon, which is 12, plus 18 times the molar mass of hydrogen, H2, which is 2, H1 is 1. Okay, so we find the molar mass of this gas is equal to 8 times 12 plus 18, whatever that value is. I'm not good at that. I didn't solve it explicitly. 8 times 12, 96, plus 18.
Should be like 114.
Big number, 6 plus 8, I think you're right. I'll write that, tell me if I'm wrong. Okay, so 114, and what are the units on a molar mass?
Kilograms per kilomole.
Kilograms per kilomole. So now, how do we use that, along with the mass flow rate, to convert that to a rate?
So make it kilomoles per minute.
Yeah, so we want kilomoles per minute, or kilograms per, kilojoules per minute for this, Q out. Okay, so Q out, Q dot is equal to Q times M dot over M. Okay, so we found M, we know M dot, so we can find Q dot out is equal to 11997.1 kilojoules per minute. I have weird units on that for some reason. That kilojoules per kilogram, that's not right. Okay. Alright, so we found part A. Now we have to find part B, and when we find part B, part C will be pretty easy to find. So the entropy generation is equal to the entropy of the products minus the entropy of the reactants plus Q out over the temperature of the surroundings. So this Q out that we found will be helpful because we can put it into this equation. We could also rewrite this that it's the number of moles in the product times the entropy of the products minus the number of moles in the reactants times the entropy of each of the reactants plus Q out over T of the surroundings. Okay, so we're going to need another table to do this. So we're going to look at our products. And what are our products in this?
H2O liquid,
Okay.
CO2.
H2O, CO2, oxygen, and nitrogen. Okay, how many moles do we have of each?
62,000.
Okay, so what's the total number of moles? We add those up, it's 84.75, excluding H2O. Because H2O is in the liquid form, it's not going to be in a combination with these other gases. So when we calculate this, we calculate it based on that. Okay, so then we find Y, which is equal to N over the total number of moles. For CO2, it's 0.0944. For oxygen, it's 0.0737. And then for the nitrogen, it's 0.8319. Okay, so then we calculate the entropy of our individual component is going to be equal to S, the reference entropy at 25 Celsius and 1 atmosphere, minus R sub U, the universal gas constant, times the natural log of this Y value for each one of those. So for our liquid water, our value is just 69.92. Because it's not an ideal gas, we just looked it up directly from the table, 69.92. Okay, O2 is equal to 205.04, that's the entropy at the reference state, minus 8.314 times natural log of 0.0737. So we find that to be equal to 226.72. For carbon dioxide, it's 213.80 minus 8.314 natural log of 0.0944. So we find that is equal to 233.43. And then for nitrogen, it's 191.61 minus 8.314 natural log of 0.8319. We find it's 193.1. Okay, so we found the actual entropy values of each of our components in the products. We need to do the same thing for the reactants. So we have C8H18, O2, and N2 are reactants. So the number of moles for those is 1, 18.75, and 70.5. And we calculate the total number of moles in this mixture to find the mole fraction. So this one, the mole fraction is 1. 18.75, 70.5 is 89.25. So then we calculate y, which is n over n sub m. For this one is 1, because C8H18 is by itself when it comes in, so it's completely that. For this, it's 0.21 and 0.79. So again, we can calculate our reference entropy minus our sub u natural log of the molar fraction. Natural log of 1 is 0, so for C8H18 it's just simply equal to the same entropy that we looked up before, 360.79. For these other two, it's 218.015 and 193.57. So again, that's taking those entropy values that we looked up at the reference state and then subtracting off this correction factor. I just didn't write that all out explicitly. Okay, so now we have the entropy values. We can actually plug them into this equation in order to determine our entropy generation. So our entropy generation is equal to the number of moles in the products. So we have 9 times 69.92 plus 8 times 233.43 plus 6.25 times 226.72 plus 70.5 times 193.14. Okay, that's the product minus the moles of the reactant. So we have minus 1 times 360.79 minus 18.75 times 218.015 minus 70.5 times 193.57. Okay, so that's this part and this part of the equation, plus our Q out, which we solved before was 5470680 over 298 Kelvin. So our entropy generation is 17792.8 kilojoules per kilomole of fuel. The rate of entropy generation, similar to what we did before, is S gen times m dot over m is equal to 39.02 kilojoules per minute. That's part B. And then part C, the exergy destruction, the rate of exergy destruction is T naught times S gen. So that's 298 times 39.02 gives us 193.8. Probably you guys can't even see this back here, but. Yeah. Okay, 2 whole boards for one problem. And again, it's a matter of being very careful in your calculations, making sure that your algebra is correct when you're determining the combustion equation, looking up the correct property values, and making sure the signs are all right on those as you start adding things together in these equations. So they can get big and complicated, but it's not that it's difficult to do, it's just you have to be methodical and careful as you go through the analysis. Okay, so any questions on this example? All good? Okay, so you like that one, let's do another one. Oh no! I think we're still gonna get out early today, but that's all right. Okay, so now we're looking at this in the practical application, because up to now, we've been looking at, steam power plants kind of separately, and now we're looking at combustion separately. Well, they actually go together, because the whole purpose of this combustion process, in many cases, is to add heat to another power generation process. So we're looking at that combined effect. So if we have a steam boiler that's heating liquid water at 200 Celsius to superheated steam at 4 megapascals and 400 Celsius, and methane fuel is what is being burned in order to accomplish that heat transfer. It's burned with 50% excess air, and the fuel and the air enter the boiler at 25 Celsius, and the products of combustion leave at 227 Celsius. So we need to calculate the amount of steam generated per unit mass of fuel, and the exergy change of the steam, and the exergy change of the fuel. Okay, so exergy change, how is it related to what we've done right now? How is exergy related to any of this other stuff?
It's how much useful we're going to be able to put into our, whatever the boiler's running.
Yes, okay, so it's a potential to do work, but I was just looking at more for this, that exergy is just T naught times S gen, so that's okay too. All right, so let's get started on another big problem that takes up a lot of space. So maybe for fun, to make it more interesting, I can have somebody else come up here and balance the combustion equation, and then we can tell them if they're right or not, and make fun of them if they're wrong. Does that sound good? Who wants to be brave? Nobody's brave. Some of this stuff will be used again, so. Nobody wants to make eye contact either. Patrick, come on up. Okay, let me find the right example.
It's only fitting for the former chemistry major.
No, I just made eye contact. Right, Leslie,
Yeah, he looked at me, so I knew. Okay. So it's CH4 coming in, methane. CH4, and it's 1.5 times the A theoretical of air coming in. And then imagine these problems, if now you don't have dry air, you have humid air, you also have to account for how come it's humid that could be.
Was that in the reservoir?
There's no water coming into the combustion process. That's the boiler we're going to look at a little bit, but we'll look at it separately. So just balance the combustion equation right now. And if you have suggestions for what you should or should not do, pipe up.
Keep doing it. Give me a suggestion. Keep doing your time.
Ran out of variables. How's he doing so far?
Sure.
Ah, good.
Whatever that is.
How did you guys?
Looks good.
Awesome. All right. So this 1.5 times 2 times 3.76 is equal to 11.28. So now we can erase the coefficients and replace them with their actual values in the equation. So it's CH4 plus 3 times O2 goes to CO2 plus 2 H2O, 11.28 nitrogen plus O2. Okay. All right, so in our previous problem, our reactants and our products were at the same temperature. They were both at 25 degrees Celsius, but for this one, we're told that our reactants come out at 227, or our products come out at 227 Celsius, which is 500 Kelvin. So now in our table, we're going to have to look up a lot more values. So we're going to have to look up the H of 298, which is our reference enthalpy. We're also going to have to look up H of 500 and S at 500. But we don't need to look it up for every component in this table because only some of them exist at those different temperatures. So we have CH4, and our enthalpy of combustion is negative 74850. We don't need to look up the enthalpy at 298 or the enthalpy at 500 because it's only existing at 25 degrees Celsius. So it would be H of 298 minus H of 298, and it cancels out of the equation, so we don't need to worry about it. But we do need to look up its entropy at 298. And if we go to table A26, we find it's 186.16. And the values for the rest of these stay the same. But it's important to note that CO2 doesn't occur at 298 and H2O doesn't occur at 298. They only occur at 500, so we don't need to look up those property values for those either. Actually, we do need these ones. Yeah. Okay, so we have to look up the enthalpies at 500 for some of these components. Which ones don't we need? I guess just the CH4. Everything else we have to look up. My table's slightly different than this one, so okay. So this is 8682. Nitrogen is 8669. CO2 is 9364. And water in the gaseous state, 9904. Then we look up the enthalpies at 500. 14770, 14581, 16828, and 17678. And then the entropies at 500, we don't need that one. 220.589, 206.630, 234.814, and 206.413. Okay, so we've looked up the entropy and the enthalpy at the inlets and the outlets. Now we can start applying some of those equations that we had previously to determine our Q value and our enthalpy value, or our entropy value. Okay, so again, Q out is equal to the summation of the moles of the products times the enthalpy of formation for each of those products, plus the enthalpy minus the enthalpy of the reference state, minus the number of the reactants, the enthalpy of formation, plus the enthalpy minus the enthalpy of the reference state for reactants. Okay, so we go through the same process that we did before, where we look at the individual number of moles of everything, we multiply them by their values. When we're looking at the enthalpy of the reactants, this cancels out, so that actually goes away because the reactants are at the reference state of 25 degrees Celsius, so we don't have to worry about those. And of course for oxygen and nitrogen, remembering that the enthalpy of formation is 0, so we only have in the reactants the CH4 and this enthalpy of formation for the CH4. So blah, 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 blah. I could write all that out. Look in the notes if you want to see it. So Q out is equal to 707,372.64 kilojoules per kilomole of CH4. Okay. What does it ask us to find for Q out? The amount of steam generated per unit mass of fuel burned. Okay, so what is this here? What does this represent, this value?
Q into the boiler.
Okay, this is Q out of combustion, which is Q into the boiler, right? So this represents the amount of heat that's released when we burn the fuel. Okay, so what other quantities do we need to figure out in order to find out how much steam is generated as we burn this fuel?
Can we just look up the heat of vaporization for the water in the boiler and that's it?
Okay, so it wouldn't simply be the heat of vaporization because it's not going
Because we need
from
to,
saturated liquid to a saturated vapor. It's going from saturated liquid to a superheated vapor. But you're on the right track. So if we look up the enthalpy values for the water, in this case in the boiler, and this water that's in the boiler is separate from this water that's in the equation. They have nothing to do with one another other than that they're both water. But the water that's in the boiler is heating up. We're told the inlet conditions and the outlet conditions. So we can look up the enthalpies for the water. So at the inlet state, it's going to be H sub F at 200 degrees C, which is equal to 852.26 kilojoules per kilogram. And H2 is going to be equal to the H at 400 degrees C, 4 megapascals. So we find that value is equal to 3214.5 kilojoules per kilogram. Okay, so we know that this difference in enthalpy is going to be equal to the amount of heat that's coming into our boiler, right? So that's the amount of heat that it takes to take this system from a liquid water to a superheated vapor. So how do we equate that to what's coming out of the combustion chamber? So the mass of the steam times H2 minus H1 is going to be equal to the mass of the fuel times the Q out of the fuel, right? Okay, what units do we have on our Q out right now? Okay, kilojoules per kilomole. We want it in terms of mass. How do we get it in terms of mass? So this is like a Q bar. How do we go from kilojoules to kilomole to kilojoules per kilogram?
Divide by molar mass.
Okay, so we divide by the molar mass. So in this case, Q is equal to this Q bar divided by the molar mass. And we can look up the molar mass of CH4 in the table, and it is given explicitly as some value, which is 16. M is equal to 16. So we divide this 707,372.64 divided by 16, and we find a Q that's equal to 44210.79 kilojoules per kilogram. Okay, this is actually with the lowercase q. They start screwing with their nomenclature in chapter 15. That's what we're in chapter 15. Where capital Q used to always be total heat, and now they're just using it willy-nilly for whatever they want. So this is like a lowercase q because it's kilojoules per kilogram. Okay, so we have kilojoules per kilogram. We're going to have kilojoules per kilogram here. So we can say that if these two are equal to one another, we want to know the amount of steam generated, so the mass of the steam generated per unit mass of fuel. So the mass of the steam divided by the mass of the fuel is going to be equal to Q out of this boiler over H2 minus H1. So the heat from the fuel divided by the heat that goes into the steam gives us our mass ratio, which if we plug in the numbers is 18.72 kilograms of steam per kilograms of fuel. Okay, so that's part A. Oh, we still have 2 more parts. That's right, because our table's already drawn. We just have to put different numbers in. Okay, so our products, we don't have liquid water in this one, we have gas. So our mole numbers are going to change. These values will change. But our procedure will be the same. So how many moles do we have of water in our products? What time is it?
305.
What time?
305.
Oh my gosh. Okay. How did I burn up all this time when I thought I would finish early? Okay, so we have 2 moles of water, 1 of CO2, 1 of O2, 11.28. So this is 15.28. We find our mole fractions. And then we do the same thing where this entropy is equal to the reference entropy minus R sub u natural log of the mole fraction. So we calculate those values, 257.49. Oops, no, that's not right. These are in a different order. 257.49. For water, it's 223.32. For oxygen, 243.26. 209.15. Okay, so then we do the same thing for our reactants, where in this case we have CH4. Our ratios are going to end up being the same, even though the total number of moles is different. It's 3 and 11.28, but our mole fractions are the same, and our values that we calculate for nitrogen and oxygen are the same, but for CH4 it's 186.16. Okay, so now we have all of our entropy values. We plug that into our equation for entropy generation, which is equal to N sub P times SP minus N sub R times SR plus Q out over T surroundings. So it's not any of these numbers, different numbers. We put them all in. We're careful with our math. We find that our entropy generation is 2656.7 kilojoules per kilomole of fuel. And then the change in exergy of the fuel is equal to T naught S gen, which is equal to negative, actually it's a negative T naught S gen, equal to negative 298 times 2656.7 kilojoules per kilomole is equal to negative 791.685 kilojoules per kilomole of the fuel. Okay, this is part C. We sort of skipped over part B, which is the amount of steam, the exergy change of the steam. So in order to find that, we need to go back to our tables. We look up the entropy values at 200 degrees Celsius. We find S sub F is equal to 2.3305, and at 400, we have 6.7714. So to find the entropy change of the fuel is equal to the entropy generation, we find that it's delta H minus T, not delta S. So we plug in the numbers for that, and for the steam we find it's 1038.9 kilojoules per kilogram of steam. And in the examples in the lecture notes, everything is all worked out. I didn't do that for lack of space and time and whatever. Also to let you guys get out of your falling asleep. So this is the basic procedure that you follow. When you're analyzing something from an energy analysis or an energy basis, you're working with the enthalpies, enthalpy of formation, the enthalpy of the actual state, the enthalpy of the reference state, and just again, keeping tables, being careful how you input those things, making sure that you've done your combustion equation correctly so that the moles balance on either side. And then you do a similar procedure for calculating your entropy changes. And again, if you keep it in a tabulated form, it's much easier to kind of keep it straight and keep track of what's going on. So you only have one homework problem that's similar to this, but you have several homework problems where you have to calculate the heat transfer or the energy out of the combustion process. Okay, so that's it for today. Have a good vacation. Be safe. If you have any questions, you can reach me by email.